Welcome to this next lecture on sound structure interaction. So we ended up here looking at the denominator and physically relating each of the terms, their origin and their meaning. Okay, and this is the denominator which will remain with us for a long time. We have to study this in detail. So let me write it. We have k fourth minus kp fourth, okay, square root of k square minus k0 square minus mu kp fourth. Okay, that is the denominator. Okay, and we said we will take two non-dimensional parameters m, which is k0 by kp, okay, and the other epsilon, which is rho c by m times the coincidence frequency. Okay, so let us see, if I divide by kp fourth, I get k fourth by kp fourth minus a 1 square root of k square minus k0 squared minus mu, okay, divided by kp fourth, right. Now here I multiply by kp and divide inside by kp square, okay. So that leaves me, first of all, k by kp is my non-dimensionalized wave number. I will call it zeta. So I get zeta to the power fourth minus 1, then a kp square root of zeta square minus k0 by kp is my m square minus a mu, okay. Then I have zeta to the power fourth minus 1 square root of zeta square minus m square minus mu by kp. Okay, so let us look at mu by kp. Okay, so mu by kp is equal to rho by m, I will say kp multiply by k0 divide by k0. Okay, so this is equal to rho by m, k0 is omega by c, okay, and kp by k0. Okay, kp by k0. So this is equal to rho c by m omega into omega c by omega c k0 by kp. Okay, so if I go to the next page, rho c by m omega, omega c by omega c, k0 by kp, okay, this is equal to rho c by m omega c into omega c by omega into k0 by kp. we said earlier that my m is equal to root of omega by omega c, or m square is omega by omega c, or omega c by omega is 1 over m square. So I get rho c by m omega c, k0 by kp is also equal to m. So I get m from here divided by m square from here. So this part is epsilon, so I get epsilon over m. So the denominator is zeta fourth minus 1 square root of zeta square minus m square minus epsilon by m. Okay, this is my denominator. This is my denominator when I try to invert Vk, or when I try to invert phi k comma y. In both cases, that is my denominator. Okay, and therefore it carries the roots for my contour integration. So let us now look at try to find the roots. We will try to find the roots, okay, using asymptotics. Okay. Now epsilon is the fluid loading parameter, rho c by m omega c is a fluid loading parameter. It carries the structural inertia in the denominator, fluid inertia in the numerator. So it's a ratio of the two inertias. Okay, so typically it's a small quantity. Okay, typically it's of the order of 0.1 or 0.2 for most material fluid combinations. Okay, so small. Now first of all, as we do in asymptotics, if epsilon is set to 0, then the denominator looks like zeta fourth minus 1 and square root of zeta square minus m square. Okay, so this is set to 0 to find my roots, right? Is set to 0 to find my roots. So now I am finding my uncoupled roots. Okay. So what are my uncoupled roots? One set gives me, or one term gives me zeta to the power fourth is 1. So zeta is equal to plus minus 1 plus minus I. You can see these are the flexural roots, right? These are the flexural roots, plate roots. The other term, xi square is equal to m square, zeta square is equal to m square, gives me zeta is equal to plus minus m. This is the acoustic wave. Okay. Now as I said, finding the singularities of this expression, that means setting this to 0 and finding the singularities of this is quite a challenging issue. Okay, why is that? Because first of all, it is fifth order and zeta. Okay, so there is no closed form formula to find it. Okay, there is no closed form formula to find roots of a fifth order. Okay, so we have to do something numerically, we have to find, or some other way. So some other way is this asymptotics. Okay, that means what is asymptotics doing? I am taking the unperturbed roots, that means I am taking the uncoupled roots. Okay, so the same logic, that I know the roots to this part and the equation is perturbed by a small quantity, therefore the unperturbed or uncoupled roots must be also perturbed in a small manner, to a small extent. So we will add a small correction term and try to find the correction. That is the logic over here. Okay. Now, so finding this is a big issue, and after finding which roots are relevant is another issue. It will come up. Okay, because as we said, causality is an important thing. Okay, causality of the whole problem is an important thing. So some roots will not obey causality and some roots will obey causality. So we'll do that discussion later. Okay, but right now, using asymptotics, let us try to find perturbations to these roots. So let us first try to find the perturbation to zeta equal to the root 1. Okay, so how do we do that? It's very simple. We choose a correction. We replace zeta with 1 plus a1 into epsilon. Okay, I can do more. I can do plus a2 into epsilon square, etc. Okay, but because I am showing by hand, I am going to take only one correction, so we will drop this term. Okay, so I am finding a correction to the plus 1 root from the plate flexure. Okay, so we substitute back into my equation. So I get 1 plus a1 epsilon to the power 4th minus 1, okay, square root of 1 plus twice a1 epsilon plus a1 square epsilon square minus m square, okay, minus epsilon by m, that is equal to 0. Okay. So in order for this to be balanced, I should find a term that has epsilon only in it as a coefficient. Only then can I balance this term because it has only epsilon in it. Okay. So we are doing order balancing. So if I, let's see, in here 1 is an order 1 term as we denote in asymptotics, that means the largest order term. Similarly, m square is an order 1 term. 1 with epsilon is an epsilon order term. The one with epsilon square is a further smaller epsilon order epsilon square term. So these can be ignored for now in comparison to 1 minus m square. But what about here? Here I have 1 plus twice a1 epsilon plus a1 square epsilon square, and this is further whole squared. So I get 1, this squared gives me epsilon squared, this squared gives me epsilon fourth, only this gives me another next epsilon term, any other gives me higher orders in epsilon. So I get plus 4 a1 epsilon minus 1. There are other terms, but they are all orders epsilon square, etc. Okay, and then this square root is 1 minus m squared, okay, minus epsilon by m is equal to 0. So we cancel this out. Okay. Now I have an epsilon order term here with epsilon coefficient. I have an epsilon order term here with epsilon coefficient. They can be balanced. So I have 4a1 epsilon, 4a1 epsilon square root of 1 minus m squared minus epsilon by m is equal to 0. So, if I take out epsilon, I get this 4a1 square root of 1 minus m squared minus 1 by m equal to 0. So, setting this coefficient equation to 0, I get a1 is equal to 1 by 4 square root of 1 minus m square into m. Okay. Okay. So, I have got my A1 correction. So, what is my corrected zeta? What is my corrected zeta? Corrected zeta is given by 1 plus A1 epsilon. So, I have epsilon divided by 4m square root of 1 minus m square. Okay. So, we should remember that zeta is a non-dimensional thing. So, it is, what is it? It is actually k over kp, right. Okay. So, if I replace it, if I say k by kp is this 1 plus epsilon by 4m square root of 1 minus m squared, okay, then my k which I am looking for, okay, is kp plus epsilon kp by 4m square root of 1 minus m square. Okay, I forgot to mention in the beginning that we are trying to find the roots of this non-dimensional denominator. As the first cut, we will do it for m less than 1 or k0 by kp less than 1, which means below coincidence. I should have mentioned that, below coincidence. So, first we are doing it below coincidence. Okay. So, 1 is bigger than m. So, if I look at my complex plane, okay, and here is my k0, the acoustic wave number, basic uncoupled acoustic wave number, and I am below coincidence. So, my kp will be higher, this k0, kp will be higher. Okay. Now, due to fluid loading, what has happened? The original kp has been incremented with a real number. The kp was a real number, it has been incremented by a small quantity. So, it moves in here. Okay. Now, because we are below coincidence, this is subsonic, this is subsonic. Okay, and we know subsonic waves do not make sound, right. They do not have a y component which can propagate. Okay. So, let us look at gamma now. What is, so phi was what? Phi had a e to the power of minus gamma y, right, e to the power minus I omega t. Okay. So, gamma related to the y wave number, right. So, we know and of course, e to the power I k x. So, we have figured out the k, which is this new quantity along the x direction, but what is the sound field along the y direction? I need gamma. So, gamma now is equal to square root of k square minus k0 squared. Okay. So which is approximately equal to, now let us see, I am going to substitute my newfound k value. So I have to put square of this, so it is kp square, and I will just take the couple term, which is plus twice epsilon kp squared by 4m root over 1 minus m squared, okay, and minus k0 square, minus k0 squared. So this goes and I get a 2 over here, okay, and I get here, if I take square root of kp square minus k0 square outside, I will get square root of 1 plus epsilon k kp squared by twice m square root of 1 minus m squared into square root of kp squared minus k0 squared. Sorry. Into kp squared minus k0 squared. Okay, so I can divide now by kp squared. Okay, so this becomes 1 minus m squared. Okay, so what do I get now? I get gamma is equal to square root of kp squared minus k0 squared square root of 1 plus epsilon by twice m into 1 minus m square 3 by 2. Okay. So for small value of epsilon, gamma is approximately square root of kp square minus k0 square, and I get rid of the root, which is 1 plus epsilon by 4m into 1 minus m square 3 by 2. Okay. So what did we find? We have phi of k comma y given by a e to the power of minus gamma y, okay, and kp is greater than k0, okay, and all others are positive quantities, m is below 1, so gamma is obtained as a positive quantity, positive real quantity. Okay, and therefore the sound field phi ky acoustic potential decays in the y direction. Okay, so this is the result of zeta is equal to 1 coupled root related to that. Okay, just remember all these will come back to us again. Now, so we have 4 roots, right? Zeta plus minus 1 and plus minus I. So let's look at what happens to the I root. Okay, so just to remind you again and again, we have K0 here, okay. Kp was beyond to start with. Kp has incremented slightly further, okay. Kp plus some delta, that's the result, okay. Now we are going to look at the IKP root, non-dimensional, I mean dimensional IKP root or non-dimensional I root, okay. So let us see then same. So zeta is equal to I plus A1 epsilon, and I can have higher terms, okay. So let me see, I have zeta fourth minus 1 square root of zeta square minus m square minus epsilon by m equal to 0. So let's substitute I. So I get I plus A1 epsilon to the power 4th minus 1, okay, and I square minus 1 plus twice I A1 epsilon minus m square minus epsilon by m equal to 0, okay. We will correct only till order epsilon, so we don't. So here again I get I plus 4 I A1 epsilon, okay, minus a 1, okay, into square root. This is a small order term, so I have minus 1 minus m square minus epsilon over m. Sorry, I fourth, okay. So I fourth is 1. So I get this cancellation and I get is equal to 0. So if I take the epsilon out and see the coefficient equation, I have 4 I A1 square root of minus 1 minus m square minus 1 over m equal to 0, so that I can write my A1 as 1 over 4I okay, 1 over 4I m square root of minus 1 minus m square, okay, or this is equal to minus I by 4m root over minus 1, okay, square root of 1 plus m square, or finally minus I by plus minus I 4m root over 1 plus m square, okay. This I goes, I get a plus minus. So next I get A1 is equal to plus minus 1 by m square root of 1 plus m square. So what is my new root near I? Zeta is equal to I plus a1 epsilon. So plus minus epsilon by 4m square root of 1 plus m square. Okay. So if we have to look at that picture, I have k0 here, I have kp here, kp got incremented to kp plus delta. Okay. Now here I have ikp. So if I make it dimensional now, let us see. Zeta is k by kp is equal to I plus minus epsilon by 4m square root of 1 plus m square. So this becomes k is equal to ikp, the dimensional root, plus minus epsilon kp by 4m square root of 1 plus m square. Okay. So that ikp, the imaginary root, got perturbed either way in the real direction. So there is a correction in this way, real direction, correction this way, real direction. Okay. But whether both are valid or not, we will see. Okay. Whether both roots are valid or not, we will see. So we have seen a correction to 1, we have seen a correction to I. Okay. We are running out of time, so let me close the lecture here. We will continue from here next time. Thanks.